When an object rests on an inclined plane, three forces come into play: gravity, the normal force, and friction. Gravity acts downwards and can be split into two components, one parallel to the surface pushing the object downwards, and one that's perpendicular, balanced by the normal force. Static friction resists motion when the object is stationary, while kinetic friction opposes movement once the motion begins. The angle of repose marks the point at which the parallel gravitational force overcomes static friction, causing the object to slide. Once in motion, the net force along the incline, accounting for gravity and kinetic friction, determines the object's acceleration. Understanding these forces is crucial in applications like transportation, construction, and material handling, where controlling motion and friction is essential.
Greetings, my name is Wan Alriz bin Wan Sarman with the matrix number of CD240212. Okay, so when looking at the inclined plane and friction, a few fundamental forces come into play, which is gravity, the normal force, and friction. Gravity pulls down on the object, but this force can be resolved into two components. One pushes it against the plane surface, and the other tries to push it down the slope. The normal force balances the push into the surface, while friction works against any sliding motion. If the object is stationary, static friction adapts as necessary to keep it in place up to a certain limit. Once it starts to move, however, the lower value kinetic friction takes over and is usually weaker than static friction. The inclination of the slope is also a factor. Steeper angles means greater gravitational force in the direction of sliding, which makes it more difficult for friction to hold an object in place. Using these concepts, we can determine at what point something will stay stationary or slide away. The table presents experimental and calculated values of the applied force required to move an object on an inclined plane at different angles. It includes 6 tests with inclination angles ranging from 20 degrees to 60 degrees. For each test, the applied force is measured experimentally and compared with the theoretical force calculated using relevant equations. The percentage difference between experimental and calculated values is also provided. The results indicate that at low angles, such as 20 degrees, there is a significant discrepancy between experimental and calculated forces, with a 50% difference. As the angle increases, the percentage differences decreases, reaching just 3.7% at 60 degrees. This trend suggests that experimental errors or frictional forces have a greater impact at lower inclination, while higher angle yield more accurate agreement between experimental and theoretical values.
Assalamualaikum, my name is Shahfiz Ahika bin Musyaharin. My metric number is CD240110. Now, I will talk about observation. Key observation is angle and friction analysis. For the first one, key of observation is angle and applied force relationship. For example, as inclination angle theta increase, the applied force P requirement overcome friction also increase. Next one is reflect the increasing gravitational force opponent along the plane. The next key point is difference between calculated and experimental values. The first one is experiment force P are consistently lower than calculated value. Possible cause because of surface flaws, instrument, calibration issue, or setup vibration. The next key point is percentage different trend, which is percentage different decrease with increasing angle. The largest difference, which is 50% at theta equal to 20 degrees. Smallest difference, 3.7% at theta equal to 65%. Next key point is angle effect on friction, which is at lower angle, friction play a significant role, leading to larger discrepancies. As the angle increases, the gravitational component dominates, reducing the difference. The last key point is friction behavior. Experimental results suggest deviation from theoretical predictions. The last one is likely due to vibration in the coefficient of friction or assumption in calculation. That's all for me. Thank you.
Good morning, doctor. My name is Zakaria Austin Anak Grunsin, and my number metric is CD240166. Today, I drew the calculation for the friction coefficient and apply force in various angular conditions. These calculations are crucial in understanding how friction and apply force with angle. So I will draw with friction coefficient. First, let's look at the friction coefficient using the formula Uthm. We find at 20 degree tan 0.364, and then second at 30 degree tan 30 degree 0.577, and then at 40 degree it become tan 40 degree 0.1839, and at tan 50 degree it's come to 1.192, and last is tan 65 degree is become 1.154. This show how friction increase significantly as the angle increase. Next, we calculate the applied force using the formula PW sin plus UW cos, assume W 0.79 Newton. The result are at 20 degree. After the calculation, we get it in 0.52 Newton. At 30 degree, P equal to 0.176 sin 30, 0.364 divide by 0.76 cos 30, it equal to 0.9 Newton. And the third one is at 40 degree, we will get 0.70 Newton, and at the 50 degree we will get 0.79 Newton, and last but not least is at 95 degree we will get 0.81 Newton. So the conclusion is illustrate the interplay between angle, friction, and applied force. Understanding this relationship is external is designing system to handle very condition effectively. This result highly how applied force increase with the angle due to the changing component of friction and weight. So that's all for me, doctor. Thank you.
Discussion. Question 1. The experimental values are consistently lower than calculated ones. Example, at 20 degrees 0.26 Newton versus 0.52 Newton is 50% differences. Discrepancy decreases at theta decreases. Smallest theta at 65 degree 3.7%. P must counteract S equals to W sin theta and friction F equals to macro W cos theta increasing with theta. Question 2. Surface irregularities and external force factors. For example, dust and vibration. Assumption of constant micro and measurement errors. Question 3. Horizontal friction depends on W unknown, while inclined friction depends on W sin theta and W cos theta. Inclined planes have critical angle for influencing motion. Force direction are simply on horizontal planes, more complex on inclined ones.
Friction on an inclined plane plays an important role in determining the motion and stability of objects. Differences between theoretical and actual results highlight issues such as surface flaws, measurement mistakes, and assumptions of consistent friction. The experiment showed that the force needed to overcome friction increases with the slope angle. This knowledge is vital in designing systems that rely on the balance of forces for performance, safety, and efficiency in fields like material handling and transportation.